Hi everyone, Mr. Smith here, and in this lesson we are talking about momentum and impulse. So let's get started. So you've probably heard about momentum, and you've probably even used this term before to talk about, say, like maybe a sports team having momentum in a series if they've won a few games in a row, for example, or something having a lot of momentum if it's kind of like on a roll and moving very fast. Momentum is a very useful concept in physics, especially when analyzing collisions. Today, we're actually going to learn the momentum and impulse is actually a more general form of Newton's second law. And actually, that's how Newton originally presented his second law. It's in terms of momentum and impulse. Later on today, we're going to talk about and investigate conservation of linear momentum. When it happens, under what circumstances, is there anything else conserved, etc. Angular momentum is something that exists, and it's the momentum that a rotating body has, and that is a kind of a complicated topic because you can have spherical objects that rotate or cylindrical objects or irregular objects too. And it's complex enough that it's usually studied in like a first-year physics course. So we'll be just talking about linear momentum. So what is momentum? So momentum is defined as the mass of an object multiplied by the speed at which it's moving. And that's actually how you calculate like the magnitude of momentum. But momentum is actually a vector, and it's given by mass times velocity. So of course, yeah, if you want just the absolute value of a momentum, you would just multiply the mass by the speed. But one thing to note, and I might even get this down if I were you, is that momentum is a vector. Okay, in brackets here, I'm going to add P equals mv, and we may use this calculation for problems where we're just kind of concerned with the magnitude of momentum. And the units of momentum, because we're multiplying mass by velocity, the units of momentum are kilograms meters per second. So if you could think about inertia as like a resistance of a body to having its motion changed, momentum is mass in motion. So before we move on, let's just do a couple simple sample calculations with momentum to give you just kind of a general idea of what kind of momentums kind of everyday objects have. So consider a really big transport truck that has a mass of 8,000 kilograms. It's traveling at 10 meters per second. Let's find its momentum. So momentum is mass, and here we're just doing the magnitude. 8,000 times 10, and those are in kilograms and meters per second. So we know we'll get 80,000, and the unit's kilogram meters per second. So obviously a very simple thing to calculate. Let's actually play around with this number a bit. So consider a turtle with a mass of 5 kilograms. This got shifted up a little bit, converting to a PDF it looks like. But what speed will this smaller turtle have to have the same momentum as the truck in the previous question? So if P equals mv, we can get V by doing P over M. So let's take that 80,000 kilogram meters per second. The turtle has a mass of 5 kilograms. So that's 16,000 meters per second. 16, I said convert it to kilometers per hour, but I mean, that's 16 kilometers per second. That's extremely fast to have that same momentum. So you can see that, small objects have to be moving very fast to have a large momentum. What's the kinetic energy at this speed? Well, that might be interesting to find. So a half, 5, 16,000 squared. And maybe we'll find the kinetic energy of the truck as well. That might be interesting to compare. So, okay, that's a lot of zeros. That looks like 640 million joules. And if off to the side, if you want to compare that with the truck, 1/2 times 8,000, and its speed was 10 meters per second squared. That's only 400,000 joules of kinetic energy. So some interesting sample calculations here. Things with the same momentum can have different kinetic energies, like you've seen here. And because kinetic energy depends on the square of the speed, momentum just depends on the speed. You can see that a smaller object can actually have a lot more kinetic energy. So would you rather be struck by a truck moving at 10 meters per second or a turtle traveling at 16,000 kilometers per second? Probably the truck, although both would probably hurt you very badly. I think the truck would the turtle would for sure just kill you. So we're going to talk about impulse next. So you may have heard the term momentum and maybe had a vague idea of what it was and what it implied, but impulse is definitely something new for the grade 12 course. Sorry, I've got the lovely City of Guelph maintenance crew is taking care of the school across the street here. So I don't know, I find the lawnmower noises to be nice and soothing, actually. Little background noise. So the momentum impulse theorem is what we're looking at next, and it's useful for solving fairly complex problems involving things that are accelerating or undergoing collisions. And it comes from looking at a deeper look at Newton's second law, F equals ma. So I mean, conceptually, I think we would all agree. So if something is experiencing a force, a net unbalanced force, it's going to accelerate. If it's going to accelerate, its speed will change. Not necessarily if it's like a uniform circular motion, but in a linear sense, in one dimension, which we're talking about, if something is accelerating, its speed is changing, and its momentum will be changing too. So we can think about Newton's second law in terms of momentum, and that's what our starting point is going to be. So we're going to start with this. So if we start with sum of forces equals mass times acceleration. And I'm going to rewrite acceleration as change in velocity over change of time. If I rearrange this formula, I get the following. And I might put a sum of forces average there, because this allows us to account for time varying forces. You know what, guys? It's gonna, if you want to pause the video, I'm just gonna go close my window. The lawnmower is just getting a little loud, and I'm concerned that it's gonna affect the video quality, and I don't want to reshoot the video. All right. And we're back. If we rearrange this formula, we get the following. The sum of forces on average. And again, the average just allows us to include maybe if the force is varying, but we're just going to be normally just using a constant force. Equals mass times change in velocity. Now, we're talking about, like, when we're talking about linear momentum right now, just for kind of everyday objects like a turtle or a truck. And, because those things just have constant mass. Later on, when we do relativity theory, we're going to see that something traveling close to the speed of light, interesting things happen with the mass. But, we have constant mass here. So m delta v is actually just a change in momentum. So what we get is, and I forgot to actually multiply this by time. So sum of forces average times time. And so we get this equation, that sum of forces times time equals change in momentum. And this change in momentum is called the impulse. Moving forward here, we have a equation for impulse. And the symbol we use for impulse is capital J. I believe I have seen some resources use an I. I think I have, but the problem with using capital I is that that's reserved for current when we talk about electricity and magnetism. So the symbol I'm going to use for impulse is capital J. And impulse is defined as basically force times time. And it is equal to change in momentum. So you apply a force over a certain amount of time, it's going to change the object's momentum. And that change in momentum is called the impulse. And again, delta P is the change in momentum. So that's like the final momentum minus the initial momentum. So this form, the form of Newton's second law of motion that we usually use, F equals ma, as we've seen, we can kind of rearrange this, which is pretty cool. And so if we rearrange that again, another version of Newton's second law is this: sum of forces equals change in momentum over change in time. And if you've taken calculus, then you could write that as force is change in momentum, or the derivative of momentum with respect to time. But of course, that's just if you've taken calculus. For you guys who haven't, and for this course, what we really need to know is this. So what does this equation indicate? The following. I don't think I have this yet. I have to write this out. What does this equation indicate? The net force in the object equals the rate of change of its momentum with respect to time. Which is pretty cool. And again, I think we'd all agree, if something's momentum is changing over time, its velocity is changing over time, which means it's accelerating, which means it is experiencing a net unbalanced force. And this equation here, and also the just different version for impulse, kind of quantifies that. So pretty cool. We're going to look at a couple of examples now. So consider we have a car that's traveling at 25 meters per second. It's coasting along a road, then it enters a rough patch, and then it decelerates to a speed of 15 meters per second in 5 seconds. So coasting implies we're not on the gas at all. So it's just kind of coasting along, and then the road itself is going to slow it down to 15 meters per second. So let's calculate the change in momentum in the car. So we're, again, for today, just looking at one-dimensional problems. So we have a car. It's going to go over a rough patch. And I'm going to choose to the right to be positive. And so we have initially speed is 25 meters per second. And then finally, its speed is positive 15. So it's still going in the same direction, right? So let's find the change in dimension, the change in momentum of the car. So let's do part A. Change in momentum. And we're in one direction here. So I'm going to drop my vector signs. And whether our final result is positive or negative will kind of indicate whether momentum is gained or lost. And it'll indicate the direction too. So we have mv2 minus mv1. Oh, you know what? I don't think I mentioned, no, we got to assume a mass for the car. So let's just make it a 1,000 kilogram car. So 1,000 times 15 minus 1,000 times 25. That's going to be 15,000 minus 25,000. That's going to be minus 10,000. So the change in momentum is minus 10,000 kilogram meters per second. So we had initially 25,000 kilogram meters per second of momentum. At the end, we only had 15,000, which means we've lost 10,000 kilogram meters per second of momentum. In terms of vectors, v2 and v1, the velocities would be to the right, the change of momentum would be to the left. But working with 1D, it makes sense to use positives and negatives to account for direction. So let's do B. So, you know what? I think I wanted to actually make, if you guys would flip back with me to momentum impulse theorem, something I want to point out. So we know the units of momentum are kilogram meters per second. Check out the units of impulse: force times time, newtons times seconds, newton seconds. Those two units are equivalent. So the impulse, remember, impulse is change in momentum, right? So impulse is equal to the change in momentum. So it's not a trick question. The impulse is also minus 10,000. But what I would like to have here is the units for impulse, thinking of it as F times T, are minus 10,000 newton seconds. And these are the same units. They are equivalent. So that's what I was getting at there. For part C, well, if we compare the units, so let's look at newton seconds for part C and just kind of convince ourselves. So the units of the newton are the kilogram meter per second squared in SI units, and then seconds. And you can see seconds divided by 1 second factor of the seconds on the bottom gives you kilogram meters per second. And you can see, hopefully I've convinced you that those two units are equivalent. And whether you want to use one or the other kind of depends on the context. If you're talking about momentum, a change in momentum, it might make sense to leave it in the units of momentum, kilogram meters per second. But perhaps if you're talking about it in terms of force and time, maybe you want to use newton seconds, but they are equivalent. So what is the average net force here? Well, now we can use the momentum impulse theorem, because impulse is force times time, and rearranging that, J over delta T minus 10,000, and it took 5 seconds. So in our question, at least the way I've set it up, we can say, hey, that the road itself, or whatever's going on that bumpy surface, slowing down the car, on average exerted a force of 2,000 newtons. So it could have made maybe a bit more at one time, a bit less at another time, but on average, that car experienced a 2,000 Newton force to the left to slow it down over time. So a nice little example to get you guys using the equation for impulse and compare some units. Let's do an interesting application. So this idea of impulse is connected to sports, and a ton of sports, any sport that kind of involves follow through. So I've got a tennis example here, so you can see Roger Federer. So we're throwing a little tennis ball in the air, and it struck right at the top of its motion. So at the top of its motion, hopefully we'd all agree. So that means that at the top of its motion, just before it comes back down, its speed is 0 meters per second. And then the tennis ball is struck, and the tennis racket, we're going to say, exerts a force of 420 newtons on the tennis ball. And we're going to, in part A, analyze what happens if that racket is in contact with the ball for 4.5 milliseconds. Then we're going to look at what happens if the player followed through with their shot. So maybe instead of hitting the racket and stopping here, maybe they follow through and they just allow themselves a split second more of contact with the ball. And then we'll see what the final speed of the ball is after each collision. So let's get started with part A. All right, so for part A, I'm going to set the problem up this way. Average force times time equals change in momentum. And I'm setting it up this way because I'm actually given the force and I'm given the time. And I'm just going to actually expand on delta P there. So we know that's mv2 minus mv1, but that's equal to 0 because the object was at rest initially. So the final speed of the tennis ball will be the average force exerted on the tennis ball times the time that it's exerted on it divided by the mass of the tennis ball. And we have all those things. So 420 newtons, 4.5 milliseconds, 0.0045 seconds, and 57 grams is 0.057 kilograms. So just being careful that those are all in our standard units, newtons, kilograms, seconds, meters, etc. So 420 times 0.0045 divided by 0.057. So that is about 33 point. I might keep an extra decimal place of accuracy just in this question. So 33.2 meters per second. If you would like to convert that to kilometers per hour, that's about 119 kilometers per hour, which, like, if you were at a tennis match, they would show you the speed in kilometers per hour. So let's change the problem up. And I don't need to re-solve for V2, but we're in part B, we're tweaking the problem, and we're going to keep everything the same, except we're going to follow through just a bit more on our shot, and we're going to use a different time. We're going to use 0.0053. So, hopefully it's obvious to see if we increase the time, we're going to increase the final speed, right? 0.057. And let's see how much of a difference this can make. So 39.1 meters per second, which is equivalent to, if you multiply it by 3.6, 140, basically 140.6 kilometers per hour. So you can see a drastic change, over 20 kilometer per hour improvement. So the idea in this example is, by following through, the player increases the time that their racket is exerting a force on the ball, which leads to a bigger change in momentum and a bigger speed when it leaves the racket. Now, this concept can be applied to baseball, golf, all kinds of sports, hockey, taking a slap shot. So if you play a sport and you've heard your coach talk about follow through, this is why. We can think about it in terms of the momentum impulse theorem. So that's a really cool application. Let's continue. So what I want to move towards is allowing you guys to handle problems where the force isn't constant, where the force might vary over time. Now, we're going to motivate that with a simpler problem, more simple, simpler, I don't know, where we just have a constant net force. And I want to make some connections with you guys. So here I want to just actually draw the force time graph, or force time profile, you may hear it called. So here we have a constant force of 8 newtons being applied to a mass for 8 seconds. And then my force time graph ends here, because after that, no more force is being applied. So let's find the impulse on the mass. So I believe I have a lot of space for you guys. You might not need all this space. So sum of the average forces times time. And like in this case, the force is just constant. So it's just simple. The average force is just 8 newtons, right? It's 8. And I might even add the units in here. And then 8 seconds. So the impulse, 64 Newton seconds. And again, that means that our change in momentum will be 64 kilogram meters per second. They mean the same thing, right? So what we're told in this question is that, whatever we applied a force this time and it sped the object up, but the final velocity is 40 meters per second. We're going to find what the initial momentum was and the initial velocity. We're just going to do it in 2 stages. You could probably just, most of you guys could probably just find the initial velocity in 1 step. Where is my cursor here? Well, yeah, we'll just do this one in a couple steps. So what's the initial momentum? So impulse is change in momentum. That's mv2 minus mv1. And we know all these things except for V1. So I'm going to solve for V1. I'll do a couple steps just because. So moving MV1 to the left, and then moving delta P to the right, we get MV1 equals MV2 minus delta P. And so V1 will be M times V2. Oh, you know what? Silly. I'm actually doing what I said. I'm actually doing B and C all at once. So let's do, you know what? Let me just finish it off. So if you wanted to do this all in one step, yeah, you could just set this up and solve for V1, and that'll give you the answer to part C. But I think I'm going to stick to my, and feel free to do that if if you'd rather not do what I'm doing. I'm actually just going to do what it says and just find the change of momentum. Because what we see here is that momentum should be gained. We should be getting a positive value here. So what's the initial momentum? So I'm going to set it up as P2 minus P1. Again, what I did before was totally fine, and that just gets part C directly. But I think my intention for this question was to do a bit more scaffolding. So we know the change of momentum, and we know P2 because we have the mass and final speed. So rearranging for P1, we get P2. So that's moving P1 to the left, moving delta P to the right, minus delta P. And so now we can do it. That's mv2 minus delta P. Squeeze this in here. It's a 5 kilogram mass. At the end, it's moving at 40 meters per second. And the change in momentum is positive, 64. So the initial momentum, that's 200 minus 64. That is 136 kilogram meters per second. And now because you know the mass, you could find the initial speed by taking the initial momentum and divided by the mass. So that's 136 divided by 5. 13.6 times 2. It's too early in the day for me to be doing that mental math. 27.2 meters per second. And of course, if you just actually finished off the problem the way I'd set it up, you get the same answer, 27.2 meters per second. But I want to, my intent with this example is twofold. Not only is this just to do something different, and here we worked backwards and found an initial velocity, is to show you a connection between the area underneath a force time graph and a change of momentum. This is just a rectangle because it was a constant force. And if you look at the area of that rectangle, 8 times 8, you just get 64. It's what we got for the change of momentum. And this is what I want the intention here. It's this. Impulse is the area under an FT graph. So, early on, maybe our first day, we reviewed distance time graphs and was like, velocity is a slope of a position time graph. And we talked about, distance traveled was area, change in displacement was area under a VT graph. Change in velocity was area under an AT graph. Well, here's just another interesting tidbit is that the change in momentum or impulse is the area under an FT graph. And we can use that for problems where the force isn't constant. So if you had some applied force, like, stepping on the brakes in a car and then kind of easing off, where it's just not, you don't go from nothing to having, an applied force on the car, it kind of gradually goes up and then gradually goes down as you take your foot off the gas. So how do we handle scenarios like that? When we can't exactly convert this into an average force where it's not obvious, what we can do is we can find the area under the graph. So here we can estimate the change of momentum, but it's basically counting squares and estimating the area. When you take calculus and maybe in your first year university learn how to do integration, you'll be able to find the area under these curves mathematically. If I gave you a problem like this, we'd have to estimate it. So I could see, 4, 12, another 4, that's 20, 22, 24. With a couple extra tidbits, I'd say maybe the area under that curve was maybe 25 or 26 Newton seconds, and we have the change of momentum. We're going to do an example where we can calculate the area because the force profile just has simple geometric shapes. So here we have an object of mass 3 kilograms, an initial velocity of 7 meters per second. We want to find the final velocity. So notice here that this force profile actually dips below the t-axis. That's to indicate that, say, if the force was acting right initially at 2 newtons, then for a brief time, that force is actually moved back to the left. So we have a time-varying force. So the force is 2 newtons, and then it decreases to 0, but then it acts in the other way, comes back above, and we want to find the final velocity for this particular force profile. And my scale didn't get messed up. Looks like it, converting to a PDF. It's 2 newtons, so 1 newton per square, and then 2 seconds, 1 second per square. Keeping things simple. So to get the change in momentum, we need to find the area under this curve. So you can break it up into, depending on your comfort level with like trapezoids, you could break this up into 3 shapes. I'm just going to break it up into rectangles and triangles. So here's a rectangle. Here's a triangle above. Here's a triangle below. Here's a triangle. So if I could find the area underneath the curve there, and I'm going to subtract off the area below, like it's like almost like a negative area because the force is acting in the other direction, I'll get the change in momentum. And so, yeah, we're just doing like a grade 9 problem, doing some composite areas. So, and everything's just one, every unit here is one square, right? So like 1 by 1. So hopefully, we don't need to write 3 times 2 for the area of that rectangle. We can see it's 6. The area of this guy is 2 full squares. Area 3 is 1 full square. We'll be subtracting it off. Area 4 is half a square, 0.5. Area 5 is 2. So 8, 7, 7.5, 9.5. And we know that area is going to give us our change in momentum. So kilogram meters per second. We now can find the final velocity. So change in momentum is mv2 minus mv1, final momentum minus initial momentum. And we can solve for v2. That would involve bringing mv1 to the right, so delta p plus mv1, and dividing by the mass. Let's finish it off, guys. Change in momentum, 9.5, 3 kilogram mass. Where am I looking? The initial velocity, 7 meters per second, divided by the mass, 3. So 9.5 plus 21 divided by 3. So about 10.2 meters per second. All right. Maybe just one little side note here. If you take this change of momentum and we using, do I do that in the next? I do that. So yeah, let's find the average net force. I didn't do it on that page. So remember, impulse, which is change of momentum, equals average force times time. We now know the change in momentum. So average force is change in momentum over time, which was 9.5 kilogram meters per second, or Newton seconds, divided by the time, which was 10. So we got about 0.95 newtons. So what that means is, for our force profile, an equivalent force profile would have been finding the area underneath a rectangle at 0.5 newtons, 0.95 newtons for 10 seconds. Those two problems would have had the same answer. So calculate the final velocity for our weird force profile. We would have got the same final velocity if we had an average force or if we had a constant 0.95 Newton force acting for 10 seconds. We'd have the same constant velocity, or the same final velocity. All right, so we did a lot in that lesson. We introduced the idea of momentum and impulse, and the big idea was impulses change momentum, and we use that to solve various problems involving a force acting on an object for a certain number of seconds. We also talked about the importance of follow-through in sports. So up next, you guys are going to do a little investigation on collisions in one dimension, and you're going to look at, hey, when two things collide, what properties are conserved? Are they conserved all the time? And you're going to look at that in terms of several different types of collisions. What we're going to call elastic collisions, inelastic collisions, and explosions. So it should be fun. That's all from me for this lesson, guys. Hope you're staying well. Have a great day, and we'll see you soon.